Hello, welcome to today's Go seminar. Today's speaker is Radovan Červený, and he will tell us something about generating faster algorithms for d-path vertex cover.
Perfect. Thank you very much for that lovely introduction. Do you know that this is actually the first Go seminar in the year of the dragon? That's cool. So let me just start the timer, and in the next 30 minutes, I would like to discuss with you something about the problem called d-path vertex cover, and maybe how we can solve it a little bit faster. But before we dive into d-path vertex cover, we need to know something about something a little bit different. This problem is called subgraph vertex deletion, F subgraph vertex deletion, and it's defined as follows. Your input is some graph G, and you are given an integer k, and I ask from you to give me some subset of vertices S of size at most k, such that if I remove it from my graph, the remaining graph will not contain any graph from F as a subgraph. Little example. This is my set F. It's just one graph path on 3 vertices, and this is my input. This is my k, and as you can see, this graph contains many free paths as a subgraph, so we need to get rid of them. So this is the first one. We can delete vertex 1, and we get rid of this. We get rid of this path. There is another path. We can delete it by deleting vertex 4, and one path is remaining. So let's delete vertex 6. Since we have deleted only 3 vertices and the starting k was 3, this set is valid for us, and the remaining graph does not contain any free path as a subgraph. It is not needed for the set to be just a single graph. It can be any number of graphs, but we require the set to be finite, because if it's infinite, then things become a little bit complicated. So what problems do we know that can be expressed as this F subgraph vertex deletion? Of course, vertex cover, where the set F is just a single isolated edge. Then our d-path vertex cover, where the set is path on d vertices, and many, many more. For example, taking cycles or cliques, you get triangle vertex deletion, etc., etc. So let's go back to the d-path vertex cover and briefly what we know about the problem. It was introduced at 2011 by Brescia, and from that point onwards, it was like systematically studied. But since it's a special case of d-hitting set problem, we get a lot of, it's not legible, but don't worry about it. We get quite a lot of results stemming from this problem, from d-hitting set. What I wanted to say that there is actually, so far, it is not known if the d-path vertex covers can be solved in something like d to the k, in something less than d to the k in general. That's what I wanted to say. And after 2011, of course, people started to worry about the problem, and they gradually improved the running time more and more. And in this talk, I will be talking about this last line here, because we were able to quite significantly improve some running times of some d-path vertex cover problems. Okay, so let's take a closer look at the results we've seen in the table. And my aim with this is to show you that many of the fastest results currently always use some kind of branching algorithm, or some kind of structures where you have to do some case analysis and work something out. And here is, for example, one of our previous results where we used 50 branching rules and we achieved something. But it is a very common method to use some branching rules and design your branching algorithm like this. So the question is, can a computer do this for us? Yeah, maybe a computer, like there is a lot of talk about AI, yeah, but that's quite imprecise for our case. But what can a computer do in this case? Well, this approach was initiated by Graham et al., who showed that this is actually possible. They, for some other problem, also a general problem, they showed a procedure that can output some branching algorithm that solves the problem, and we do something similar. But we kind of restrict ourselves, and that allows us to improve the algorithm. Like, we do not solve as many problems as they did, but we solve them faster. So what do we typically look in the generating algorithm, the one that generates the algorithm that solves the problem? Well, we need that no human input is needed during the computation. Yeah, it will be kind of apparent why this is needed, because you don't want to sit at the computer and tell it what to do. Of course, we want to say to the program, I want this algorithm to be this fast. Yeah, and of course, in an optimal case, we would also get some proof that the output is correct. Yeah, not just the algorithm itself, but some description that the output is correct. Yeah, I will show it if I have time at the end. And yes, the output algorithm should be simple. In other words, it should not depend on the length of or the number of branching rules that we have generated. Yes. And why is that? Well, more is always better, and these are our results. And for example, I mean, with 3 branching rules, you get this, and maybe if you use 100,000 more, you can do it faster, right? Yes. So that's why, for example, no human input is needed, and no, it should not be required, because probably no, it's not just humanly possible to analyze this algorithm. That's what I want to say. But I want to show you this graph. Yeah. So these are the fastest algorithms we were able to generate with our procedure, but this is just the fastest one. I can generate anything in between. And this graph shows you the blue line is the number of rules in the numerical algorithm, and on the x-axis is the target branching factor. And as you can see, I can quite literally, for any branching factor, I can give you some algorithm. Yeah, it might not be as efficient as the best one, but the number of rules is, for example, 1,000, better than 1 million or something like that. Yeah, and also the time it takes to generate 1,000 rules is just a fraction, an instant it takes to generate 1 million. Yes, that's what I want to say. That I have in the beginning. I've shown that we have our previous work. We have shown for the decay algorithm with 50 rules. It took us several months, to prove it, right? And in 0.2 seconds, you can generate something faster with 200 rules, and it is the same, quite fast. Okay, so how do we approach it? What do we do? So there are 3 parts: some basic building blocks, and how the output algorithm looks, and then what the generating algorithm does. So our building blocks is something we call a subgraph branching rule, and it is some kind of restricted branching rule. And in this rule, what we need is some graph H. Some of these vertices will be red, and then we will prescribe how do we branch on this subgraph. And how do we apply this rule to graph G? We look for an occurrence of this graph in our graph. So, for example, like this. But there are some conditions. We need that the red vertices do not have any neighbors outside this occurrence. So, for example, the first condition is that the occurrence is an induced graph. As you can see, there is no edge here, so this edge is bad for us. So this is not an occurrence of this subgraph rectangle. This looks better, but we require that these vertices do not have neighbors outside this yellow graph, yeah. And then we find this occurrence, and this occurrence is okay. So we can apply our branching. And what do? We go one by one, each branch, just delete them and recurse. Yeah, go to another branch, delete it, recurse. Yeah, typical branching algorithm. The complexity of the resulting algorithm given this rule is given by some equation, and what you get from this equation is some branching factor, some number that describes how much this rule branches. And the smaller this number is, the better. So that's our basic building block. So how do we put them in the output algorithm? So let's assume that we have already some list of generated branching rules, and we do the following. First is a typical stopping condition. If the instance is already trivial, then we can answer appropriately. Yeah, for example, if we have exceeded our budget, then we say no. Yeah, come on. Now, if each component is small, we can just brute force the result. Yeah, each component is small. Just use any algorithm that you can think of. It will probably run in FPT time, and will be good. Sorry, in polynomial time, no. Yeah, and how small it should be? Well, it depends on the largest graph in the list of the generated group. And otherwise, some component will be large, and in that case, we will find some rule in the list that can be applied to this component. And we do the branching, we recurse, and we probably will get rid of this large component. Yes. So for the output algorithm to be correct, we need to make sure that in the list there is always at least one rule that can be applied to this large component. Yeah, and we will ensure that somehow. And of course, this is the implementation requirement. We require that this output algorithm stays the same regardless of how long this list is. That's an implementation thing. Just an example how this list of the branching rules can look. Yeah, it will be given in some machine readable format. You can just, it's a compressed archive, for example, and each line will describe the graph, vertices, edges, the red vertices, and the branches, something like that. Of course, you can think of some binary encoding, whatever, but this is sufficient. This is also semi-human readable. Okay, so we have our basic building blocks. We have our output algorithm. So how do we get this list of generated groups? So this is basically it. The input of the generating procedure are just these two things, or maybe three. Yeah, we will see. And so this is the set of forbidden subgraph that's in the problem definition, and then the target branching factor. We will start with two lists, one good and one bad. The good is empty. The bad contains some initial set of graphs, which is based on F. And then, while we have something in the bad list, the graphs in the bad list correspond to graphs we have not yet processed, or we do not know any efficient branching for them. We use something like expand. Then, for each graph in the list, we color it, and then we generate some rule for it. And if the rule is efficient enough, we move it from the bad list to the good list. Yes, and you can see if this while terminates, we will be left with an empty bad list. Something will be in the good list, and we will be sure that everything in the good list, the branching factor is what we want, and the rules are correct. Simple, right? Yes. So these three things are the things that are the interesting ones. Yeah. So what expansion is? Okay, so we think about it that we are trying to design a branching rule for some graph, and we are stuck. We don't know what to do. So what we want is maybe look a little bit further. Maybe if we add a vertex to our structure, maybe we can find something new, pattern or anything. So the expansion takes the bed list, and to each graph in the bed list, we will add a vertex in every possible way. By doing this, we will get some larger graphs, and we will just concatenate these lists, throw away the isomorphic ones, because we want just one occurrence of each graph in the list, and then we will throw away anything that is already handled by our good list. Yeah, because this good list corresponds to structures that we already know how to get rid of. We already have some branching rule for it. So if we expand our bed list and we see that, for example, this guy is still here, we can get rid of him because we already know that we have a rule for him. So we do not have to process it again. Yes, and this is the expand step. We will, by doing this, we retain that. That's not important. By doing this, we allow ourselves to look at larger graph and potentially have a better branching into this graph. Okay, so the color function is what is actually our main contribution, or one of the main contribution of this paper, which is very different from the approach of Grammetal that I was, or improvement upon the approach of Grammetal, I should say. And what is it? So assume that you have this is the graph of the subgraph branching rule, graph H, and you are interested about this vertex V. And you are interested in a question whether if I find an occurrence of this graph into graph G, if this guy will have some neighbors. Okay, so what we can do is to take this graph and we look at all expansions, all supergraphs that said that the extra vertex is a neighbor of V. Yeah, so we will generate these graphs where the extra vertex is a neighbor of V. And now we look if there are some good branching rules already that can handle these structures. And if we see that all of these structures are already handled, well, that means that if we find this occurrence into graph G, then it cannot have a neighbor, because that would mean that some other rule can be applied, and we can apply the rule instead. Yes, and that's the point of the color function. And what we get these annotations where we can be sure that if we find and we look for it in the graph, then the red vertices won't have any neighbors outside the graph H. And this is different from Grammetal. This allows us to design more efficient branchings with it, because now you know actually about something about the input graph that is not known beforehand, right? Yes, this is basically what I just said. So yeah, okay, so we have annotated, we have expanded our list, so we have larger structures that we can look at. We have annotated these structures with these red vertices, and this is the input for the. Now we are ready to generate the actual branching group, the branches. Again, this is a three-part process in our case, and the first is the minimal solutions, and this is basically the most naive thing you can do to ensure that the branching will be correct. what can you do is you take your graph and you enumerate all subsets of vertices of this graph, and you leave only sorry, I'm getting ahead of myself. To design a correct branching rule, it suffices to enumerate all subsets of vertices that are solutions to this graph. Yes. For example, 1, 2, 5, 1, 2, 5. If I remove from this graph 1, 2, 5, what remains does not contain, in this case, I believe it's path on 5 vertices. Yeah, or it does not make any sense. Like maybe 2 vertices. Okay, sorry, it's my fault. Yeah, but if I were to remove, let's say, just 5, yeah, you can see that it just remains, so it's not a solution. Okay, so once we enumerate all solutions to this graph, we want to keep only those that are inclusion-wise minimal. Yeah, because yeah, we go through them one by one, but there will be some subset that already contains some smaller subset, and it does not really make sense to keep this as a branch because it is already like subsumed by this one. Yeah, we are making progress towards the same solution if we branch by this branch instead of this one. So we just eliminate them, throw them away, and what we are left with is the minimal branches for this graph. Yes, and this is our starting point, and we are going to optimize this list somewhat. And this is this second step we call dominance between branches, and again is probably the second main contribution of this paper. And what we do in here, we compare the branches pairwise and look at them what they do. Yeah, so in this example we will compare branches 1 to 5 and 2 to 5. And what if we delete just part of the branch? Well, we will start with the 1 to 5. Let's delete the vertices 2 and 5. Okay, looks good. So we continue by deleting the vertex 1, and this looks good. Like nothing inefficient so far, nothing out of the ordinary. Okay, so let's do the same with the second branch. We again delete these vertices 2 and 5, and then the branch tells me to delete vertex 3. But you probably already can tell that this is not really efficient. Like this is not the right thing to do, because this vertex is red. It ensures that it has no other neighbors other than this guy here. So deleting it does not make sense. It is much better to delete the vertex 1, right? And just move this, just instead of 2, delete 1. And it's better for us. No? Well, but if we do that, we get this 1, 2, 5 branch, but we already have this in our list. Okay, so if we can somehow ensure that this branch 1 to 5 remains in the list, then this branch is not needed. And this dominance is what allows us to significantly prune the list of the minimum rules, because they are typically very inefficient. They do not use the information in the red vertices. That's why they're inefficient. So from the minimal branches, what we do is we will have some elimination order, which we will ensure that is valid. It's not important how we get there, and we will filter the branches that are dominated by some other branches. And what we are left with is dominance-free branches. Okay, and the last thing, what is a good thing to do, is something we call adjustment, and this is a very, again, naive, trivial heuristic. How we can improve the branches, and it's basically this. We can try to improve the branching by introducing some new branch. Yeah, I mean, introducing any branch is always correct. Yeah, you just do more work, But if you introduce some good enough branch, for example, in this case, if I add branch 1, then basically what I can do is delete every other branch that contains 1 as a subset, because again, the 1 will go towards the same solution as the branches that contain. Okay, and in this case, the result is a branching rule with only 1 branch, basically a reduction rule in this case. And we do this with all the branching rules until no improvement can be achieved. And this is actually, this is really heuristic. If anyone from you feels like you can solve this exactly, it's some, I don't know, weighted something, set cover, but the weights are like functions or something like that. It would be a great help to this algorithm. Okay, so that was how we generate these branching rules. Now you may ask if this is all necessary for our algorithm, and yeah, it is necessary. This graph compares the generating algorithm if I choose to turn off some of these features. Yes, and in here it's not very visible, but if you do full algorithm, if you do nothing, like no dominance, anything, you just get stuck at 5. It does not do much. If you do full algorithm without something I call handmade rules, I will get to that. You again will not go far. But if you just use the handmade rules, again you don't get far. You need everything. I don't know. It's probably the algorithm is bad. You need everything. So what are these handmade rules? It's something that I can put into the generating algorithm, and it will help. Basically, these are like handmade reduction rules that apply in some cases, and we have found a way that how to encode it to the algorithm so that it can use this information during when it decides if the branching rule is handled or not. Yes. So let me give you an example of what I mean. So this is one of the reduction rules we use, and if you look at this, again, this is I think 5 path vertex cover. If you have a situation where there is a single vertex and there are some components connected to it, and just it, and these components do not contain the path on 5 vertices, then it kind of makes sense to just leave one of these components, and reduce the graph. Okay, that's the intuition. And how do we apply this reduction rule, which is it is designed to work for the input graph, right? Just let it run on the graph. It is not designed for these subgraph branching rules. But again, that's where the red vertices come in, because if these components would be red vertices, then I can be sure that even in the input graph they do not have neighbors. And now the reduction rule would apply in that case. So I can consider this structure handled in the generating algorithm, and I do not need to care about it anymore. Again, I will, in this case, I would just, I would move it from the bad list to the good list, but I would just say that it is already handled by some handmade rule, by who made the rule. Okay, so that's the end of the presentation. So let me quickly go over what we have done. So the red vertices and the dominance between branches are the main contributions of this paper, and we have in some cases improved improved running times of algorithms for 3 to 8 path vertex cover. And let me just a little bit of commentary. You may see this discrepancy that, for example, we have somehow stopped at this moderate number of branching rules. Why don't we go further, right? Well, we are limited by resources. The local supercomputer just does not have enough memory. Yeah. So maybe if we can buy more RAM, we can push this further. If you allow me just a few more minutes of your time, 5 more. What I want to show you is the proof. Yes, I was saying, I can give you 1 million rules, and I say, this solves your problem. You will probably say, I don't believe it. And of course, we do not, maybe there is a bug in the implementation. Yeah? We cannot know. So what we try to do is together with the algorithms, we generate some proof that quote can be verified by a human if you have enough time, or maybe enough humans. I don't know. And this is what it looks like. And basically, this encodes all the decisions the generating algorithm took to arrive at the result. This is just for 3.07 branching factor, which is a little bit slower than the 2.9, but it has only 1,500 proofs instead of million. So let's look at this. And there is the set of the initial graph, so I can just click on this graph. In this case, this is some path. And since the algorithm didn't generate any branching proof for this, it has to do the expansion. Yeah, in here you can find all the possible ways how can you expand this graph, and you can follow the path. For example, if I wanted to expand vertices 0 and 1, then I can follow the path. I can even show some isomorphisms. Yeah, let's maybe not get into details. It would be longer than 5 minutes. Yeah, and you can like follow the expansions and until you arrive at, for example, this. Yes, this still needs to be expanded, but if I try to expand vertices 0 and 1, it says that it was eliminated. Okay, what does it mean? It means that we already at that time had some branching rule that would apply in this case if we expanded vertices 0 and 1. That's what it means. And I can give you this rule, it's rule number 402, and I can give you the isomorphism such that you don't even have to like brute force the isomorphism, right? You can just verify that this, okay, this really is, this really applies in this case. Okay, I believe you. Okay, I believe you. This is the rule that solves this case. Yeah. So if we do not go here, but we instead go to here, yes, we can already see that we get some red vertices, and in this case, the algorithm determined that this can be handled or is handled by the red component reduction rule, and I can again see how the rule should apply. The proof gives me what are the components, yes, and what I should delete. Basically, it says that the red component reduction rule would apply in this case. Okay, and 2 more. If we go here. Okay, so this is again our graph, and this is actually a branching rule. And what I now have to do to prove to you that this is indeed a correct branching rule, if I use these branches, yeah, if you see this in your graph, you just have to branch on 0 and 1 and 3. quite obvious, right? Well, the thing what I have to do is, for each subset of vertices, I have to tell you what's with the subset. Yeah, so for example, a subset 1 is not a solution, and I can show you the path. Yeah, sure. 0 and 1 is a solution, but it is not minimal because we say that 0 is a branch, so 0 and 1 is not minimal, and so on and so on. And then, for example, 1 and 2 is again a solution, but it is dominated by someone else, again by 0. And since domination is not a trivial thing, I have to again show you how the domination works so you can verify it. Yes? And this is basically it. And I have probably exceeded my time with this, so I will leave it at that. And yeah, one more thing that I have to say, that the generating algorithm is some quite big C++ code, parallel, yeah, not something we want to write. But the verifying algorithm is a much more simple, a few lines of Python code. Yes, and the idea behind this proof is that the verifier is much more approachable for a human. So probably you will be sure that in the verifier there are no bugs in the verifier, and you can run it on the proof, and the proof basically says that the generated algorithm is correct. That's what was the idea. So yeah, with this I think I can conclude the talk. Thank you for your attention. Yeah.
So it seems to me that most of the algorithm you used wasn't really for d-PVC discovery, but it could be for the general problem. Just the handmade rules were for the instructor.
Yes.
So it can be like just use a different set of handmade rules, and it could be really good.
Yeah. Yes. Exactly. I didn't say it explicitly, but the generating algorithm works for any set F. We just chose to apply it to the Vertex cover because we have some experience with it and we knew some reduction rules for it. But yeah, what changes is the set F and the handmade rule. I should add that we have tried to apply it to other problems, for example, the triangle vertex deletion, I think, but it does not work. It does not generate any good algorithms, and we don't know why. Something to think about.
So maybe a brief question, but if you consider writing something like for an automatic prover to prove just the algorithm is indeed
Automatic prover?
Like yes, something like that.
Like what?
Like Agra.
Or lean. Yes. Like basically a software which basically you write
I
random
see.
proof, it verifies that the proof is correct, and it would of course be more readable than
Sure. I mean we looked into it, but it was kind of more complicated than just a few lines of Python code. Yeah.
That's why I said it's a great question. But
Yeah. I mean, it would be better because I guess you can somehow formally prove that the verifier is correct, and then we would believe it even more.
I can ask, I was just wondering if there is a known overbound for the problem for this like expected verifier.
I don't think there is. And this is actually a great question because this generating algorithms kind of it makes you believe that I give it any branching factor, and if it runs for long enough and has enough memory, maybe it will someday output something. Yeah, but this is some this should not be possible, right? Because there are some complexity assumptions that probably prohibit this. So what I'm trying to say that this we do not know for some branching factor if this algorithm stops or not, and we probably won't know for which branching factors it stops or not, something like that. Yeah, something like that.
So just to really clear to got the results by just plugging in a branching factor, and after a month you came back and say, oh, this runs for too long, so maybe try a bigger one. Just like that, or
basically like this. Because this is kind of more experimental than theoretical, but yeah.
We rather start from the big one and as long as it was successful.
Yeah. You just go a little bit fast, just a little bit. Yeah. Maybe if there are no other questions, I just want to close with something to think about, because these proofs where I just give you like million cases for you to verify, you may argue that these computer proofs are just not like good enough for real science, for example, like this. But if let's say 1,000 proofs, 1,000 proofs is still doable by one human, right? It will take him 10 years to do. Okay, Dusan can do it in 1 week. So, but does it really change your opinion on these generated proofs if it was generated by a human or by a computer? Yeah, if you gave me 100 PhD students, they would generate an algorithm with 10,000 rules. Would you believe it more, or would you believe this procedure? Something to think about. Yeah, depends on the student. Yeah, and the procedure was written by an associate professor. Okay, that's everything from me, and again, thank you for your attention.